Here's some notation we would like to introduce. So let's say you have a non-empty set A. The set of permutations on the set A is denoted S of A. So let's say I have a set A equals x1, x2, right? Just two elements. So S of A would be the set of all functions from A to A such that F is 1 to 1 and on to. So all 1 to 1 functions that go from A to A, basically. Yeah. So SA would consist of permutations. Let's list them out. So you have the identity permutation. It takes x1 to x1 and x2 to x2. So I will call that the first element of SA. And then the second element we'll call sigma 1, defined as follows. x1 goes to x2 and x2 goes to x1. So sigma 1. And it turns out that there are no other permutations. There are just two permutations when you have two elements in your base set. So your base set is A. Your base set is A, so you only have two permutations on A. The identity and what I'm calling sigma 1, or we don't even need the sigma 1 here, we can just call it sigma. So sigma basically just sends x1 to x2 and x2 to x1. Just what you call a transposition. Okay, so what we like to do here, we like to show that the permutations on a set A form a group under functional composition. So here's a theorem. Theorem. Let A be a non-empty set. The set of permutations on a set A is a group under functional composition. That circle is functional composition. Okay, so we're going to prove this. Proof. So let's consider, let A be a non-empty set. That means a set with at least one element in it. So you know you always have the identity permutation. So note I of x equals x is a permutation. Let me write it this way. I of x equals x for all x. Is a permutation, right? The identity function, it sends each element to itself, right? It sends x to x, is a permutation, right? It's a 1-to-1 onto function on the set A. So thus, I, the identity permutation, is an element of SA, set of permutations of A. Hence, SA is non-empty. So first you need to show that SA is non-empty. Then you want to show closure under the operation, which is composition. We show SA is closed under functional composition. So that means if you take two arbitrary permutations, their composition has to be a permutation. So let's let alpha and beta both be permutations on A. So be elements of SA. Then that means alpha and beta are one-to-one onto functions on A. Important. So first, we show that the composition alpha composed with beta is one-to-one. So let's take two elements, x1 and x2 in A, and let's suppose that alpha composed with beta of x1 equals alpha composed with beta of x2. We're trying to show one-to-oneness. So we're going to let the functions be equal. We want to show that x1 equals x2 here. So let's note alpha of beta of x1. That's how you define alpha composed with beta of x1 is alpha of beta of x1 equals alpha of beta of x2. That's how functional composition is defined. Now, since alpha is one-to-one, right, it's a permutation, so it's one-to-one, then that means beta x1 must be equal to beta x2, right? The inputs must be equal. The inputs are beta x1, beta x2. And since beta is also one-to-one, then that means the inputs into beta must be equal. Then that means x1 equals x2. So we started off with alpha composed with beta of x1 equals alpha composed with beta of x2. And we've shown that the inputs are the same. x1 equals x2. So therefore, alpha composed with beta is a one-to-one function. And now we have to show that it's onto as well. Second, we show alpha composed with beta is onto. Right, that's what you need to show something's a permutation. One-to-one onto on the set A. So we're going to take an arbitrary y in A. And we're going to show that there's something that alpha composed with beta sends to A, some x that alpha composed with beta sends to A. So because alpha is onto, so since alpha is onto, then there exists, or there is, let's call it some z in A such that alpha of z equals y. Right? If you're an onto function, if alpha is an onto function, for every element in the codomain, so for every y in A, you can find some z in the domain such that alpha of z equals y. Now, since beta is also onto, right, it's a permutation, then there is some, let's call it x in A, such that, nose running, beta of x equals z. Okay, so it follows that if I take alpha and compose it with beta, and I plug in x into this function, what will I get? Well, the way this is defined through functional composition, alpha of beta of x. Remember beta of x, so I'm going to leave the alpha alone outside. What's beta of x? Beta of x was z. But what's alpha of z? That's y. What I've been able to do, I've been able to demonstrate that I can plug in x into alpha composed with beta and get y. So for every y in A, there's an x back in A, such that alpha composed with beta of x gives me y. So therefore, hence, alpha composed with beta is on 2. Okay, so that shows closure under the operation. Why does that show closure? Where we've shown that alpha composed with beta is a 1-to-1 onto function on A, so therefore it's a permutation. So hence, alpha composed with beta is an element of SA. It's a 1-to-1 onto function on A. My nose is running. Okay, let's do a second part to that. Let's show that functional composition is a, what do you call, associative operation, 2. We show functional composition is associative on the set of permutations on A. So let's take 3 elements, alpha, beta, and gamma, that are permutations on A. So 1-to-1 onto functions that go from A to A. And if I were to take an arbitrary x value in A and look at alpha composed with gamma, alpha composed with beta composed with gamma of some x value from A, what would this mean? This would be, use your definition of functional composition, we're going to leave this alpha composed with beta alone. So let's just look at the blue composed with the gamma. That would mean alpha composed with beta of, right? Of, where's my baby blue color? There it is. Of gamma of x. So gamma of x is the input into the alpha composed with beta function. So that's an input. You're plugging in gamma of x as an input into the alpha composed with beta function. Now what does that mean then? That means, unraveling the definition of functional composition between alpha and beta, it's going to be alpha of, I'll call this one green here, alpha of beta of gamma of x. What happened to my, there it goes, my pen. Are you kidding me? My pen disappeared. There it goes. Now that's one way to do the functional composition. And another way to do the functional composition is to first do alpha composed with, and then beta of gamma. And then plug in some x. So what does this mean when we do the beta of gamma afterwards like that? And then an alpha out front like that. So that means you're going to have alpha of beta composed with gamma of x. So beta composed with gamma of x is the input into the alpha function. Oops, wrong color. This is going to be alpha of, and then inside of the alpha function, that input, you can unravel that definition as beta of gamma of x. But that's exactly the same thing as above, right? Alpha of beta of gamma of x is alpha of beta of gamma of x. So thus, these two things are going to be equal. So thus, therefore, alpha composed with beta composed with gamma is going to be the same as alpha composed with beta composed with gamma. Yeah, these are going to be the same permutation because they send the x's to the same places as outputs. What else do we have to show? We've showed non-empty. We've shown closure under the operation. We've shown associativity of the operation. We have to show there's an identity element. We show SA has an identity elements. Well, what's the identity element? It's the identity permutation. Let's say note the identity permutation that sends every element to itself. X to x is 1 to 1 and 1 to. So the identity permutation is an element of SA. So you have an identity element. Let's actually show it works as the identity. So we're going to compose it. Let's take the identity and compose it with alpha. Okay, so let me go back. Let me say let alpha be any permutation. Let alpha be any permutation on A. Then when I take the identity and compose it with alpha, I should get back alpha. Let's see. Okay, and we're going to let x be an element of A. So I take an arbitrary permutation, alpha, and any element x and A, and I take the identity composed with the permutation alpha and evaluate it at x. That's going to be what? The identity of alpha of x. But what does the identity do to alpha of x? It sends alpha of x to itself, right? It sends every element to itself. So identity sends alpha of x to alpha of x. And also, if I take alpha composed with the identity evaluated at x, that's going to be what? Alpha of the identity of x. Now, what's another name for the identity of x inside there? It's going to be x. So notice we have I composed with alpha is alpha, and alpha composed with I is alpha. So thus, I composed with alpha equals alpha, and alpha composed with I equals alpha. So you have to show that identity works on both sides. Works on the left side and the right side through functional composition. Okay, so we have the identity element. We want to show inverses. We show SA has inverses for each element. So let's take an arbitrary element in SA, and the permutations, let's call it alpha. Alpha. So an arbitrary permutation. So a very important fact is that one-to-one onto functions always have inverses. Since alpha is one-to-one and onto, then there is some alpha inverse in SA. So one-to-one onto functions always have inverses. Now let's compose alpha with alpha inverse. to take alpha, compose it with alpha inverse, and plug in x from A. This is going to give us what? Alpha of alpha inverse of x. And it turns out that they undo each other. So let me just draw a little diagram here. So here you have A. Here you have an x. Here you have a y. It's going to be a y right there. So alpha takes x to y, and alpha inverse takes y to x. No, I should be putting a y right here. Rather than an x, I should be inputting a y. Okay, it's not writing. There it goes. So alpha inverse, that's this dude right here, that's taking y to x. So alpha inverse of y is going to be x. But then alpha is going to take the x back to the y. Yeah. So notice that alpha composed with alpha inverse of y is y, and this is just another name for what? I of y, the identity of y, right? Y equals I of y. And also, we can compose the other way. Alpha inverse composed with alpha. Let's do a red x here. No, it's supposed to be red. So let's say I start off with the red x. There's going to be what? Alpha inverse of alpha of x. X is red. It's alpha inverse of, what's a of x? A of x here, so I take x, and I'm going to go forward to y, and what's alpha inverse of y? Well, alpha inverse takes y back to x. In other words, I of x. So thus, therefore, alpha composed with alpha inverse is the identity, and alpha inverse composed with alpha is the identity. Yeah. So that shows inverses, and that's it. Therefore, the permutations on A are a group under functional composition.